Welcome to our microlearning video. The periodic table represents the fundamental building blocks of matter, the chemical elements. Elements are pure substances that cannot be broken down into simpler substances through chemical means. They are the most basic units of matter. Compounds are formed when two or more elements chemically combine. Compounds have different properties than the individual elements that make them up. Mixtures are physical combinations of two or more substances, where the substances retain their individual properties. Mixtures can be separated through physical means. Understanding the differences between elements, compounds, and mixtures is crucial for comprehending the diverse world of chemistry and materials around us. Matter is the fundamental building block of the universe, composed of atoms that combine to form molecules and larger structures. Atoms are the fundamental constituents of matter, with measurable physical properties like mass, volume, and density. Matter can exist in different states, solid, liquid, or gas, and can undergo chemical changes that alter its composition and properties. Understanding the fundamental nature of matter is crucial for fields like chemistry, physics, and materials science. This slide provides an overview of the key concepts related to the introduction of matter, setting the stage for a deeper exploration of its properties and transformations. Solid matter has a fixed shape and volume, with atoms tightly packed in a rigid, crystalline structure. Solids exhibit high density and are generally incompressible. Liquids have a fixed volume, but take the shape of the container they are in. Liquid atoms are loosely bound, allowing them to flow and be easily compressed. Gases have no fixed shape or volume, with atoms/molecules moving rapidly and randomly. Gases are highly compressible and can expand to fill any container. These three states of matter, solid, liquid, and gas, represent the fundamental ways that matter can exist. Elements are pure substances that cannot be broken down into simpler substances by chemical means. They are the fundamental building blocks of matter. Common elements include hydrogen, oxygen, carbon, nitrogen, iron, and gold. The noble gases, such as helium, neon, and argon, are chemically unreactive under normal conditions. Elements can be classified into metals, nonmetals, and metalloids based on their physical and chemical properties. This detailed periodic table shows the classification of elements into these three categories, with clear labels and color coding. The fundamental building blocks of an atom are protons, neutrons, and electrons. Protons are positively charged particles located in the nucleus of the atom. Neutrons are neutral particles also found in the nucleus. Electrons are negatively charged particles that orbit the nucleus in specific energy levels or shells. Together, these three subatomic particles make up the structure of every atom. Understanding the role and properties of protons, neutrons, and electrons is crucial for comprehending atomic structure and the behavior of matter. The periodic table is a fundamental tool for understanding the chemical elements that make up our world. It organizes the 118 known elements based on their atomic number and chemical properties, allowing us to predict how they will behave and interact. The table displays key information about each element, including its symbol, atomic number, and atomic mass. This visual representation of the elements is essential for studying chemistry and understanding the building blocks of matter. The clean, modern design of the periodic table image on this slide provides a clear and engaging visual aid for the audience. The atomic number is the number of protons in the nucleus of an atom, which determines the element's identity. The atomic mass is the total mass of protons and neutrons in the nucleus, usually reported with the average mass of all the atom's naturally occurring isotopes. These two properties, atomic number and atomic mass, are fundamental in defining the unique identity of each element on the periodic table. The slide provides a pie chart showing the atomic number and atomic mass for several common elements like hydrogen, helium, lithium, beryllium, and boron. Emphasize how these basic properties are essential for understanding the nature and behavior of different elements. Chemical symbols are one- or two-letter abbreviations that represent the elements on the periodic table. They provide a concise way to identify specific elements. Chemical formulas use these symbols to show the composition of a compound. The formulas indicate the type and number of atoms present in the compound. Systematic naming conventions help us understand the identities and structures of chemical compounds based on their formulas. This allows for clear and unambiguous communication about chemical substances. A compound is a pure substance made up of two or more different chemical elements chemically bonded together in a fixed proportion. Common examples of compounds include water, H2O, carbon dioxide, CO2, table salt, NaCl, and methane, CH4. Compounds have distinct physical and chemical properties that are different from the individual elements that make them up. Compounds are represented by chemical formulas that show the type and number of atoms present. The three main types of chemical bonds are covalent, ionic, and metallic. Covalent bonds form when atoms share electrons, creating stable molecules. This is common in organic compounds like water and methane. Ionic bonds occur when atoms transfer electrons, forming positive and negative ions that are attracted to each other. This is found in salts like sodium chloride. Metallic bonds arise from the delocalization of valence electrons, allowing them to flow freely. This gives metals their characteristic luster, conductivity, and malleability. The visual diagram on the slide provides clear representations and explanations of these three bond types. The periodic table is a powerful tool for understanding the elements that make up binary compounds. To name a binary compound, we first need to identify the two elements present. Next, we need to determine which element is the cation, positive ion, and which is the anion, negative ion. There are specific naming conventions we can use based on the cation and anion to properly name the compound. For example, we can use prefixes like mono-, di-, tri- to indicate the number of atoms of the cation. Understanding these naming conventions is crucial for being able to communicate clearly about binary compounds. The mole is a fundamental unit in chemistry that represents the amount of a substance. 1 mole contains Avogadro's number, which is 6.02 times 10 to the power of 23 particles, whether atoms, molecules, or ions. Molar mass is the mass of 1 mole of a substance and is a useful way to convert between mass and moles. For example, the molar mass of water is 18 grams per mole, so 1 liter of water at room temperature contains 55 moles of water. The mole is a fundamental unit in chemistry that represents the amount of a substance. 1 mole contains Avogadro's number, which is 6.02 times 10 to the power of 23 particles, whether atoms, molecules, or ions. Molar mass is the mass of 1 mole of a substance and is a useful way to convert between mass and moles. For example, the molar mass of water is 18 grams per mole, so 1 liter of water at room temperature contains 55 moles of water. A mixture is a combination of two or more substances that are not chemically bonded and can be separated by physical means. Homogeneous mixtures have a uniform composition throughout, like saline solution or brass, copper, and zinc. Heterogeneous mixtures have a non-uniform composition, like a salad, different vegetables, or sand and water. Common examples of mixtures include air, seawater, alloys, and many household products like toothpaste and ink. The image on the slide provides a helpful visual diagram showing the different types of mixtures and examples. Homogeneous mixtures are uniform in composition, with no visible boundaries between the components. Examples include saltwater, alcohol solutions, and air. Heterogeneous mixtures have distinct, non-uniform components that can be visually identified. Examples include sand and water, oil and vinegar, and trail mix. The key difference is that homogeneous mixtures appear uniform, while heterogeneous mixtures have distinct, identifiable components. Understanding the difference between these two types of mixtures is important for many scientific and practical applications. Separation techniques are critical in many scientific and industrial processes. Filtration is a physical process that uses a porous medium to remove solid particles from a liquid or gas. It's effective for removing larger insoluble particles from a mixture. Distillation is a purification process that separates liquids based on their different boiling points. This allows you to isolate the components of a liquid mixture. Chromatography is a separation technique that uses the differential migration of components through a stationary phase. This allows you to separate and identify the individual components in a complex mixture. Together, these three techniques provide powerful tools for purifying, separating, and analyzing chemical substances. Solubility curves are graphs that show the maximum amount of a solute that can dissolve in a solvent at different temperatures. Solubility refers to the maximum amount of a substance that can be dissolved in a given amount of solvent at a specific temperature. The relationship between temperature and solubility varies for different substances. In general, solubility increases as temperature increases, but the specific curve can differ. This slide includes a detailed illustration of a solubility curve, annotating the key features and relationships. Understanding solubility curves is important for many applications, like crystallization, precipitation, and controlling the concentration of solutions. Concentration units are important for understanding the composition of solutions and mixtures. Molarity measures the moles of solute per liter of solution, a common unit for solution concentration. Molality measures the moles of solute per kilogram of solvent, independent of temperature. Mole fraction is the ratio of moles of a component to total moles in a mixture or solution. Understanding these different concentration units is key for working with chemical systems and reactions. Colligative properties are changes in the physical properties of a solution due to the presence of dissolved solutes. Boiling point elevation. Adding a solute increases the boiling point of a solution by lowering its vapor pressure. This requires more energy to overcome the increased intermolecular attractive forces in the solution. Freezing point depression. Adding a solute decreases the freezing point of a solution by interfering with the formation of the solid crystalline structure. These colligative properties have important real-world applications, like using antifreeze in car radiators and salt to melt ice on roads. Ideal solutions behave according to theoretical models, with no interactions between solute and solvent particles. They follow Raoult's law and exhibit predictable colligative properties. Real solutions are more complex, with interactions between solute and solvent. They deviate from ideal behavior and may show nonlinear changes in properties like boiling point and osmotic pressure. The key difference is that real solutions have interactions between solute and solvent, while ideal solutions do not. This leads to deviations from the theoretical, predictable behavior. Understanding the distinction between ideal and real solutions is important for accurately modeling and predicting the behavior of solutions in chemistry and related fields. The image on this slide shows three beakers representing different types of solutions: saturated, unsaturated, and supersaturated. A saturated solution is one where the maximum amount of solute has dissolved and any additional solute will not dissolve. An unsaturated solution can still dissolve more solute without becoming saturated. A supersaturated solution contains more dissolved solute than a saturated solution, often achieved through changes in temperature or pressure. I'll use these visual examples to explain the key differences between these three types of solutions. Colloids are heterogeneous mixtures where small particles of one substance are dispersed evenly throughout another substance. Colloids can be classified based on the state of the dispersed phase and the dispersing medium, such as sols, emulsions, foams, and gels. The dispersed phase refers to the substance that is evenly distributed throughout the dispersing medium. The dispersing medium is the substance that surrounds and supports the dispersed phase. This slide provides a clear definition and overview of the key concepts related to colloids, setting the stage for a more detailed discussion. Colloids are heterogeneous mixtures where small particles of one substance are dispersed evenly throughout another substance. Colloids can be classified based on the state of the dispersed phase and the dispersing medium, such as sols, emulsions, foams, and gels. The dispersed phase refers to the substance that is evenly distributed throughout the dispersing medium. The dispersing medium is the substance that surrounds and supports the dispersed phase. This slide provides a clear definition and overview of the key concepts related to colloids, setting the stage for a more detailed discussion. Colloids are a type of mixture where small particles are dispersed throughout a medium, like in milk, paint, or ink. Colloids have many useful applications in our daily lives due to their unique properties and behaviors. For example, the foaming agents in shampoos and the smooth texture of latex paints are made possible by colloidal dispersions. Colloids provide enhanced stability, texture, and functionality to a wide range of consumer products. This slide provides an overview of some of the common everyday applications of colloids. We'll dive deeper into a few key examples in the next slides. Diffusion is the movement of molecules from an area of high concentration to an area of low concentration. Osmosis is the diffusion of water across a semi-permeable membrane from an area of low solute concentration to an area of high solute concentration. Equilibrium is the state where the concentration is equal on both sides of the membrane. Diffusion and osmosis are fundamental processes that drive the movement of molecules and the balance of solutions in biological systems. Diffusion allows substances to spread from areas of high to low concentration, while osmosis facilitates the flow of water across semi-permeable membranes to equalize concentrations. Temperature is a key factor that affects reaction rates. Higher temperatures generally increase the kinetic energy of reactant molecules, allowing them to collide more frequently and with greater force, thus speeding up the reaction. Catalysts provide an alternative pathway for the reaction, lowering the activation energy required. This leads to a faster reaction rate, as the reaction can proceed more easily. Increasing the concentration of reactants provides more colliding molecules, resulting in a higher frequency of successful collisions. This in turn leads to a faster reaction rate. Increasing the surface area of reactants, such as by crushing or grinding solids, allows for more contact between the molecules. This increased surface area also leads to faster reactions. Catalysts are substances that increase the rate of a chemical reaction without being consumed or altered themselves. They provide an alternative pathway with a lower activation energy, allowing reactions to proceed more quickly and with less energy input. This makes chemical processes more efficient and cost-effective. Catalysts can be classified as homogeneous, in the same phase, or heterogeneous, in a different phase. Enzymes are an important class of biological catalysts that are highly specific and efficient. Catalysts are used extensively in industries like oil refining, chemical manufacturing, and pharmaceuticals to accelerate reactions and produce desired products. They are also crucial in many living organisms for biological processes. The fundamental principles of conservation of mass and energy are critical to understanding many scientific phenomena. Mass is never created or destroyed in chemical reactions. It is simply transformed from one form to another. Similarly, energy can change forms, but the total amount of energy in an isolated system remains constant over time. A closed system is one where matter cannot enter or leave, but energy can be exchanged. The total mass and energy within a closed system stays the same. These principles have far-reaching implications across fields like chemistry, physics, and engineering. Understanding them is key to explaining and predicting many natural processes. The periodic table is the fundamental organizing system for the elements, providing key information like atomic number and mass. Different types of chemical bonds, like covalent and ionic, determine how atoms combine to form compounds with unique properties. Understanding the three main states of matter, solid, liquid, and gas, and how they transform is crucial for many chemical processes. Separation techniques like filtration, distillation, and chromatography allow us to isolate the components of complex mixtures. Mastering these core concepts provides a strong foundation for understanding more advanced chemistry topics. We've covered a lot of ground in this presentation, from the fundamental building blocks of matter to how elements, compounds, and mixtures shape our world. The key takeaways are that understanding these basic concepts is crucial for making sense of the physical universe around us, and applying this knowledge can help us address real-world challenges. As we move forward, I encourage you all to continue exploring this fascinating field. Consider how the principles we've discussed could be leveraged to develop new technologies, solve environmental problems, or advance scientific discoveries. There's still so much to learn, but by building on the foundations we've covered today, I'm confident we can make meaningful progress and uncover new insights about the material world. Let's use this knowledge as a springboard to tackle the challenges of tomorrow. I'm excited to see what we can accomplish. See you in our next video.